Welcome back to the lecture series on uniform convergence. So in the previous lectures we have discussed some theorems and properties and all these things. Now we will see some problems based on MN test. So now that as I specified, we will make use of MN test to check whether the given things are convergent or not. Here for all this case, what is the thing that you can find out? So if you notice, your absolute of Rn cosine n theta would be smaller than or equals absolute of Rn product with 1. So you will have absolute of Rn and your R lie between 0 and 1, therefore you can simply have it as Rn. So by choosing your Mn to be Rn, be it any series in the given question, by choosing Mn equals Rn, you can very well see that your summation Mn converges here, right? Summation Mn converges. Therefore, the given series all should converge for all real values of theta. Moving to the next problem. These given series converge uniformly for all real values of x if summation An is absolutely convergent. Okay. Here, let us just consider the case. Absolute of An x to the power 2n or 1 n whatever we have. This 1 upon x to the power 2n. This would be smaller than or equals absolute of An x to the power 2n upon 1 plus x to the power 2n. And if you just take out x upon x to the power 2n outside and cancel, you will be left with this quantity, and this is bounded by 1. So this is what you have. So if this quantity, that is if your summation An converges absolutely, then by Mn test, that is by choosing Mn to be absolute of An, we can just conclude this thing. Supposing that if we have n here, what is going to happen? So when we have x to the power n here, okay, from this we will take x to the power n, we will take x to the power n outside, so it would be 1 upon x to the power n plus x to the power n. This gets cancelled for all real values of x. That is what we are talking. So no matter, either this will make us close to infinite or this will make us go to infinite. So as a whole, this will go to 0. Okay. So when it is going to 0, we can say that it is somehow bounded by 1. Okay. And that with that guarantee, again by choosing Mn to be absolute of An, we can just justice the uniform convergence. And for this problem, can you identify what would be our Mn? By choosing Mn to be 1 upon n times of n plus 1. This is comparable with 1 upon n square, and hence it is uniform convergent. Okay. So for this case, you can choose your Mn to be 1 upon n to the power p. And for the next question, here if you just see here also, you can choose your Mn to be 1 upon n power p. And here if you notice, it is summation 1 upon n to the power x. They are saying that it is uniformly convergent in this excuse me, this is comparable with 1 upon n to the power p, and for p greater than 1, it is convergent. Right? So with that ideology, we come to a conclusion that it will be uniform convergent in this interval. Moving further, here we have a problem. We are asked to test the convergence, uniform convergence of this given series. So from this, we will have to identify what is the general term. Okay, what is our Fn of x? This we need to identify. Okay, in the first term we have 1 plus x square. In the second term we have 1 plus x to the power 4. And it is in the third term we have 8. So 1 is producing 2 and 2 is producing 4, 3 is producing 8. So tentatively we get 1 plus x to the power 2 power n. This we are getting. Am I right? Okay. So this 2 to the power n can also be like x square, x to the power 2 to the power n. So this can be written as x square to the power n. Okay, and this shall be simply written as x to the power 2n. This way also we can write, isn't it? Okay. And in the denominator, what we have? We have whatever the quantity that we have, that is 2 to the power n, and x to the power this 2 to the power n minus 1. So this is our general term. Okay. So we shall have it as 2 to the power n. This is 2 to the power n. Okay. And moving further, when we just take the absolute value of this quantity, what do we get? That is absolute of fn of x would be equal to absolute of 2 to the power n x to the power 2 power this quantity divided by, and x is bounded by half. So even when we proceed it, we will be having only 1x that will be there in the denominator. So upon doing all these things, this is what we have. Okay. And yes, this alpha is some quantity which lie between 0 and half. Therefore, the series on the right hand side converges. By using m-test, we come to a conclusion that the given series is uniformly convergent on the given interval. Moving further, there is a typo. That is when 0 less than p less than or equals 1 and p plus q greater than 2. Okay, anyway, that typo will be clarified when we proceed further. Under this case, so our general term, our fn of x is x upon n to the power p plus x square n to the power q. This is, and it is given that, okay, so from here when we take x outside, so here in the denominator also we can just take x outside, or I don't think we don't have to take x outside. P is greater than 1 and q is greater than or equal to 0. So we will have x upon, when we take this x to the power p outside, we will have 1 plus x square times of n, 1 upon n to the power, we have taken p outside and q is there, so minus q. This is what we will have. So this 1 upon n to the power p we have as it is, and whatsoever that is there, from this we will get, and we are saying that it is in the interval a b. So whatever is the maximum of absolute of a and b, that will be our alpha. Okay, so it is bounded by that quantity because x is present on both the sides, and this will make us go to go near 0. So we don't have to worry too much. This, like the denominator part, this 1 upon x square upon n to the power p minus q is would be greater than or equals 1. When it is greater than or equals 1, 1 upon x square upon n to the power p minus q would be less than or equals 1. Therefore, this entire quantity will be less than or equals absolute of x. So absolute of x will take, now we are talking about the absolute of x. Therefore, whether it is a or b, that we don't know. We are talking in some general thing. Suppose if we are in this interval minus 5 comma 3, even though 3 is the bigger value, absolute of minus 5 is bigger than absolute of 3. So therefore, absolute of x will take the maximum value of 5. That is why we have this alpha is maximum of absolute of a comma absolute of b. That is how we get this one. Now that we know summation 1 upon n to the power p converges, therefore that is going to imply that this will be convergent for P greater than 1, and here P is greater than 1 only. Hence by M test this series converges. The next case is when P lie between 0 and 1, 1 included, and P plus Q is bigger than 2. Here our Fn of x is x upon n to the power p plus x square n to the power q, and p is somewhere between 0 and 1. P plus q is greater than 2. So here we need to do something to find out the maximum value. So for which purpose, what do we do is that we can consider this as some function of x, apply your maxima minima ideology, so identify the extreme value, and that is how we get this point. Okay, and so therefore this is what is happening, and we know the p plus q is bigger than 2. When it is bigger than 2, so obviously the power of this n is bigger than 1, therefore it has to be convergent, and hence by M test we conclude that the given series is also convergent uniformly on the specified interval. Next we are about to discuss something called Abel's test, that is if Bn of x is a positive monotonically decreasing function for each fixed value of x in some interval, and this function is bounded for all values of n and the concerned x, and now we have a convergent uniform convergent series summation un of x. Then with the when we multiply the corresponding terms of this Bn of x and un of x and form a new series summation Bn of x un of x, that will also be uniformly convergent. That is what we need to prove. Here it is given that Bn of x is bounded for all values of n and x. That means we would be able to identify one bound k such that all these things are happening. And now it is given that un of x converges uniformly. Then by Cauchy criterion for uniform convergence, this is what we have. Okay, so basically it says that summation I runs from 1 to a particular quantity n. Okay, ui of x minus summation I runs from 1 to some n plus p. Instead of taking m, and we will have to impose the condition that n is smaller than m, instead of that we just write it as n plus p ui of x, and this is less than epsilon. That is what we usually take, but this epsilon has to be a small quantity, so that small quantity can be any quantity. That is why we just divide this by k for our convenience. If you notice, all these n terms in the first term are present in the second term as well. That is why they get cancelled and we are left with this quantity. Now we will make use of Abel's lemma. What does this lemma state? If Bn is positive monotone decreasing sequence and k denote the least and greatest value. Okay, that is we are choosing k and big K. Maybe we shall just choose k1, k2 denote the least and greatest values of the sums. Summation r running from m to p u r for p equals m. Then for p less than or equals m, then what will we have is that bm product with k1 less than or equals summation r running from m to n br ur would be bm with k2. This is what our Abel lemma says. When we just employ this lemma to this situation, to this series. Okay, now that we just have proved that this UR is also bounded. So with that quantity we have the first term, that is Bn plus 1 of x, and the maximum, that is the bound of this quantity. What is the bound of this quantity? That is epsilon upon k. And this Bn plus 1k, it is since Bn is a bounded sequence, it is bounded by the quantity k. That is what we have taken. Now that we just proved it is smaller than epsilon. Now again, using Cauchy criterion for uniform convergence, we just conclude that this series is uniformly convergent. Now as we have a corollary to this result, a uniformly convergent series summation un of x, this will remain uniformly convergent. That means, okay, under what scenario? If each term is multiplied by a function, if each term is multiplied by a function an of x, provided that the sequence is uniformly bounded. What do we mean by uniformly bounded? For all x in the interval and for all n, we should be able to identify a unique bound. Okay, whenever we say it is bounded, that means either we are fixing n or x. We are not fixing both. Like when we fix both, it turns to be a single value. When we fix only one quantity, then we get a boundedness, not uniform boundedness. When we vary both x and n, what we get is a uniform bound. And moreover, this function is monotonic. If under all this scenario, what we have is your summation an of x, un of x converges uniformly. This is what this corollary tells you. Okay. Now, if you we may not be able to prove this completely, but I can give you the hint of the proof. Okay. For that purpose, what we are doing is that under the given conditions, that this an of x is uniformly bounded. Uniformly boundedness will imply boundedness. Okay, and it is monotone as well. So basically, this an of x is monotone plus bounded, which implies your an of x is converging pointwise. Okay, now we shall define Bn of x to be, and it is converging pointwise to some a, let us say. That is, limit n approaches infinity, an of x is a. We are defining a new sequence Bn of x to be a minus an of x, or Bn of x is an of x minus a. Accordingly, whether it is increasing or decreasing, accordingly we define this one. So basically, we want to retain this Bn of x to be some positive valued function. Okay, now if you notice, summation Bn of x, un of x, this converges uniformly according to our Abel's theorem. So now that what do we have? We have summation un of x converges uniformly, and summation Bn of x, that is what? A minus, without loss of generality, supposing that I have considered this case, un of x converges uniformly. Now what can I do? My summation an of x, un of x can be written as a combination of these things, right? Like from here I can write it as uh, summation a times of okay a my that is summation bn of x un of x minus summation, okay, maybe minus here, and plus a times of summation un of x. This is uniformly convergent. This is uniformly convergent. Therefore, this has to converge uniformly. That is how we complete the proof of this corollary. And the next corollary is when we have a power series which converges for all x, where x like this has some radius of convergence, then the power series will converge uniformly if and only if summation an r to the power n converges. Okay, I am not going to prove this corollary, that I am leaving to you guys. Now we shall just examine a few examples based on this Abel's test. Okay, here if you notice, this quantity converges. Am I right? Because it is positive, monotone decreasing, bounded, everything is there. And the remaining part, that is minus 1 to the power n upon n, is converging uniform. It converges basically. Okay, it does not involve x, therefore it has to converge uniformly as well. So now using Abel's test, what can we do? We can just conclude that summation minus 1 to the power n up, okay, so basically this absolute of x to the power n, this also converges uniformly. And we have another series when it converges, summation an converges, that indicates that that is converging uniformly because that does not involve x. And we observe that this 1 upon n to the power x is positive, monotone decreasing, bounded by 0 and 1 and all these things. And we apply Abel's test to confirm that summation an upon n to the power x converges uniformly. That's it. Thank you.